Welcome to my presentation. My name is Zhengke Wang, come from Tongji University. Our proposal is attention-guided unsupervised learning of monocular visual inertial odometry. In this study, we focused on following three problems. First, fusion strategy. Most existing learning-based VIO concatenate visual and inertial features together to feed into a fusion net. However, these features come from different domains and may lead to inconsistency during integration. Thus, we fuse them based on attention mechanism. That is like IMU asks a question and images answer it. A good odometry should produce stable prediction over long sequence. We designed two attention branches to solve this. Spatial and temporal branch focused on frame-to-frame prediction and sliding window respectively, and together they predict the results. At last, given only acceleration and no velocity as input, IMU module will suffer from scale ambiguity. So, we design an extra module to extract velocity information as constraint for IMU encoder. Now, let's go through the structure of our network. The inputs are images and IMU data. There are three steps to predict frame-to-frame pose. First, we deal with raw images. With pre-trained depth net and flow net, we can get depth map and flow map. These maps contain information about motion. We concatenate them together with raw images and extract visual features from them, denoted as visual memory. Visual memory between t-1 to t, and that within a sliding window, will be inputted into two fusion branches, respectively. Next, we deal with IMU data. It's quite simple. IMUNet basically is LSTM with a linear layer. Warm start module here adds extra constraints to IMUNet, which is velocity information. Here we get inertial features, also noted as kinetic query. Finally, with visual memory and kinetic query, two attention branches together predict the pose of equal car. In this work, our main contributions are integration strategy, two attention branches, and warm start module. So let's move on to the inside of these three modules. First, I want to talk about integration based on attention mechanism. Attention mechanism is introduced by natural language task. The core idea is to find something you want. For example, if we want to learn about IV and look for videos, we may type IEEE IV 2022 in the search box. That is query. Here we find a video. Its title begins with IEEE IV 2022. It implies that we should probably click into it and take a look at this video. Here the title is noted as key, and the video itself we called value. We can then compute attention with this formula. It will check if the key matches query. Moreover, there could be more than one video on the result list, and attention mechanism helps to decide if we should watch them or not. Okay, now come back to problems of odometry. IMU data is one of the input. It's a vector of acceleration and angular velocity. Describes the motion in 6 degrees of freedom. Well, the output, the pose, also has 6 degrees of freedom. There is a strong relationship between output and IMU input. So, we extract query from IMU data. It's like what we type in the search box. Meanwhile, we also have raw images, depth map, and flow map. There are several channels in visual features, like we have a list of videos. Attention module will search in the visual features to find out what is related to motion in 6 degrees of freedom, with the help of IMU query. As for attention block, we follow an encoder-decoder structure. where encoder mainly processed visual features and decoder does integration work. There are several layers in encoder, and they share the same structure. They are composed of self-attention and a feed-forward net. Similarly, decoder layers first process kinetic query by self-attention and then integrate them with visual features. Both key and value come from outputs of encoder. They are added to each decoder layer after multiplied by different weights. Here, much-head attention is utilized to generate more predictions. The formula is on the right side. This is our fusion strategy. As mentioned just now, we designed two branches to improve scale consistency. They have the same structure, the encoder-decoder form. The only difference is input, more exactly, visual inputs. Spatial branch focused on frame-to-frame prediction, so its visual memory comes from time t-1 to t, while temporal branch takes visual inputs within a sliding window. IMU input for both of them is from time step t. Then we concatenate outputs from two branches and feed them into feed-forward net to predict pose. On the one hand, our goal is to predict frame-to-frame pose, so we need a spatial branch. On the other hand, there are some landmarks that exist in multiple frames. Temporal branch helps to generate stable prediction over long sequence. As for IMU module, given only acceleration and no velocity, it may suffer from scale ambiguity. So we try to add velocity information to the input. And this information can be extracted from previously predicted pose. We designed two ways to compute velocity features. First one, the handcrafted feature, which is actually the velocity itself. It's the average velocity between time t-1 and time t. And another one, we compute it with a simple CNN. Finally, they are added together to the hidden states of IMUNet. In this way, IMUNet is able to learn about current velocity. Okay, now we come to the evaluation part. We perform experiments on kitty datasets, compared with other VO and VIO, both traditional and learning-based methods. Metrics are relative translational and rotational errors. Generally, we are the best in comparison. On the right side, here are also predicted trajectories as well as ground truths. Here the ablation study on two branches and warm start. The left figure shows trajectories of different methods. The difference occurs in the circled area. From the video, we can see that the Eagle car slows down rapidly because of the truck in front. It's a challenging scenario because the velocity of Eagle car changes rapidly, and there is a huge moving object in the view. It means that the camera provides less effective information. The temporal branch introduces historical information from images, and warm start module can utilize the previously predicted pose. From the table, we can see that they both help to improve the performance in this challenging case. At last, the robustness test. First, the test on polluted IMU data. We add extra white noise to IMU, both accelerometer and gyroscope. There are two figures shows the translational and rotational errors. It can be seen that the proposed VIO still performs well when accelerometer noise is up to 3 and gyroscope noise is up to 0.5, which are quite large noises in the real world. And there are other tests on blurred images, temporal unsynchronization between two sensors. In total, compared with wings, our method is more robust to polluted data. Thanks for your attention.